now Nima's lecture, please.
All right, guys. All right, so let's remember the k equals 1, NMHD 3 is this formula that looks like sum of R invariants, this interesting 1i plus 1, j plus 1. The very first thing that I want to do is talk about a toy version of this problem, where we'll get a somewhat better idea of the kind of thing that might be behind this. So my toy version is, instead of having R invariants involving 5 guys, I'm going to have R invariants involving 3 guys. And my z's, instead of being my z's, instead of being z at I equals 4 vectors, are going to be, I don't know, little z's, little i's, which are just 2 vectors. Okay? And so this thing is going to be delta squared of eta 1, 2, 3 plus cyclic. Okay, so I hope you see this as some kind of like slightly simpler analog of the 5-component R, right? We just sort of dropped everything down by 2. Okay? And my amplitude here, quote-unquote amplitude, not an amplitude, but my toy model for an amplitude is now just going to be the sum of 1i plus 1. Oh, and my physical poles, my analog of physical poles, instead of being I plus 1, jj plus 1,
Nima.
are just going to be I plus 1.
Nima.
Yeah. Oh, shit. Yes. I'm showing my age. I don't know if these people know who Madonna is. I barely know who she is, but I'm not. All right. Okay. Is that okay? It's on. All right. Very good. Okay. So this is my sort of toy model for an amplitude. And the kind of simplest version here would be for n equals 4, where this formula would be m n equals 4 is 1 I plus 1 could be 2, 3, plus 1 I plus 1 could be 3, 4. Okay? And let's see again, what are the poles of this guy? The poles of this guy are 1, 2, 2, 3, and 3, 1. This one is good, this one is good, this one is bad because it's not consecutive, right? And the poles of this one are 1, 3, 3, 4, 4, 1. This one is bad, this one is good, this one is good. Okay. So we have some kind of object. It's not manifestly cyclically symmetric. Okay, it's written in this way. It has a spurious pole, 3, 1, that cancels between 2 terms. And otherwise, it has physical poles, 1, 2, 2, 3, 3, 4, 4, 1. Okay. Now, just impressionistically, where have we just seen that 5 hours ago today? Does that remind you of anything? Very just impressionistically, what does it look like? Where did we see something like 1, 2, 3 plus 1, 3, 4? Right, we triangulated a square. Okay? swear to God, I keep picking this up. All right. All right. So okay, this is, again, just sort of impressionistic, but let's see. It's like we have, fundamentally, we have a square, 1, 2, 3, 4. And we've sort of triangulated it as 1, 2, 3 plus 1, 3, 4. Okay? And every boundary of the square corresponds to a pole of the corresponding R invariant. Okay? Clear enough? Right? Now, in a moment, of course, we're going to see that this is not a mere analogy. The R invariant is literally a canonical form for a triangle. Okay, so but for the moment, I want to first just define objects and talk about some simpler things before we get to that. And so anyway, all these qualitative things are, you know, there's one spurious pole, it cancels between the terms. I could triangulate any way I want, I'd get the same answer. Okay, so those are all manifest. And actually, in this case, what about for general n? For general n, what does the sum of 1 plus 1 look like? The sum of 1 plus 1, just sort of by this analogy, looks like taking a polygon and taking this one very special triangulation of it where 1 is, the point 1 is special, and I just triangulate everything going from 1. Okay? Is that clear? All right, so somehow the object that's associated with this amplitude, now I haven't told you yet about getting the function, but morally, just at the level of pictures, the object associated with the amplitude is a polygon, right? So what we want to do is generalize a polygon to higher dimensions. Except somehow, of course, a polygon is any old polytope in 2 dimensions looks like a polygon, okay? But of course, in higher dimensions, you see a really crucial part here was the ordering. I had the ordering 1, 2, 3, 4 going around. Really, that was really, really crucial. So if we go to higher dimensions, it's not obvious how to make a polytope whose vertices are ordered. Like you have some 3-dimensional, 4-dimensional, higher dimensional shape. What does it mean to make the vertices ordered in any way? Okay, that's the question. All right, so now there's a very canonical way to talk about an ordered polytope, and it turns out to be a very special and very famous kind of polytope called cyclic polytopes, and that will actually be the simplest example of the amplihedron and the simplest object that's going to give us what we want here for the next case of NMHV. But I want to build up to it. I want to build up to it by really first understanding the polygon properly. A very big part of this business is to pretend that you can't see. Okay? We do a lot of things by drawing pictures, and there's a huge amount that's sort of implicit when you're drawing pictures. But it turns out to be very, very useful to try to say, even though the pictures are incredibly useful, of course, to try to say as directly, sort of algebraically, algorithmically, if you like, as possible what exactly that you're doing without having to draw a picture. Pretend that you're blind. So how would you describe to someone? Like here we said, oh, we draw the polygon 1, 2, 3, 4, and just without thinking, we drew it with 1, 2, 3, 4 as the kind of vertices that went around, you know, this nice convex polygon. What if you couldn't see? What if you couldn't see? What if I just handed you the vectors? You know, it's a vector -1, 3, pi, e, pi squared, -4, right? And I hand you this random set of vectors. How do you know? How do you know? Is it convex? Is it not convex? Like, how should I order it? Right? That if I plot them, I can see. But how do you decide without seeing? Okay. Well, To do this, let's first talk about how I think about the points in the interior of a triangle. We used to joke with Yara that for 3 years, every one of our talks started by drawing a triangle. I could actually start with an interval, but I'll do a triangle so it looks a little more, slightly more exciting. All right, so how do I talk about the points in the interior of a triangle? So like literally, let's say this has some coordinate, I don't know, little z1, little z2, little z3. And so any point inside here, let me call it y, any y looks like a positive weighted combination of the external points. So I'll write this as C1 Z1 plus C2 Z2 plus C3 Z3 divided by C1 plus C2 plus C3. Okay, so that's just the weighted sum so that the weights add up to 1. And it's crucial here, of course, that the C's are positive. Right? So that's what we talked about before. The notion of an interior crucially involves this idea of positivity. Now, the first thing that we're going to do is to say all of this much more elegantly by thinking projectively. Okay? And again, we won't do projective space boot camp, but we won't need it in all of its gory, non-gory, in fact, glorious detail. I just want to motivate it in the following way. See, there's something very ugly here, which is divided by C1 plus C2 plus C3. So I just want to do something which just looks nicer. So what I'm going to do is elevate these z's from little 2 vectors to a 3 vector, capital ZA, which is, let's say, 1 in the top component and ZA in the bottom component. So this capital I now runs from 1 to 3. Okay? But the important point is that whatever I do with these ZAs should be invariant under rescaling. Okay, so that's what it means that it's projective. So in particular, I can always use the T to rescale the top component to 1 if I like. Okay, and that brings me back to the original picture. Okay, so far so good? So there's no information loss. Okay, I can take this configuration of 2 vectors and just lift them into 3 vectors. The usual picture of projective space is that these are lines through the origin in 3 dimensions. But anyway, we won't rhapsodize about what it all means just because all we're doing is this very simple operation. Okay, but now also y gets promoted to some capital Y, which could again be 1y, but where y is equivalent to t times y, same kind of rescaling, right? But now the interior is now something nicer. Now it's just y is equal to C1 Z1 plus C2 Z2 plus C3 Z3. There's no divided by C1 plus C2 plus C3 anymore. Okay? Do you see why? Because this, for example, if I wrote these as 1z, the top component would be C1 plus C2 plus C3. The bottom component would be C1 Z1 plus C2 Z2 plus C3 Z3. And this would be equivalent to 1 and then C1 Z1, C3 Z3 divided by the sum of the C's. Okay, so already talking about the interior of a triangle, I think about the points more nicely in projective space, but I think about 3 vectors up to rescaling, and the notion of the interior is this much simpler one. Okay? Now again, when any bit of any kind of geometry you ever do that does not explicitly invoke a Euclidean notion of distance is vastly superior to do it in projective space rather than just in thinking in Euclidean space. But let me just give you just a couple of examples. So again, everything that we do is going to be invariant under 3 by 3 linear transformations. SL3 transformations on these Zs. Okay. And so the only tensor that we're going to have is the epsilon tensor. So let's say you have 3 points, Z1, Z2, Z3. Again, the only kind of special configuration that they could be in is if they were collinear. And if they're collinear, it means that this bracket Z1, Z2, Z3 has gone to 0. Okay? So let's say I drew a triangle like this. Again, and I'm talking about the inside of the triangle, it doesn't matter. But let's say I have a point Y. What does it mean if this point is actually on the line 1, 2? It means that Y, Z1, Z2 has gone to 0, for example. Okay, where that bracket is again just contracting with the epsilon symbol, or more prosaically is just writing the 3 vectors one after the other and taking the determinant. Okay, so far so good. So the interior of a triangle is just this simple notion. So actually, since we're here, let's actually just keep on going. Now, remember, we had talked earlier today about if you have the interior of a triangle, and I wrote it like this. We had said, what is the canonical form for this triangle? And we said that omega was like dx dy over x, y, 1 minus x minus y. Right? But what if I gave you a random other shaped triangle with a random other set of lines? Of course, we could work it out, but what I want to do is actually think about this projectively again. So I want to imagine that I have a triangle. Now the projective coordinates are Z1, Z2, and Z3. And now I have some y. And now I want a 2 form in y space, right? I want a 2 form in y, which is the canonical form for this triangle, right? So whatever it is, it has to have a pole when y goes on the line 1, 2, 2, 3, and 3, 1. Right? So let's just write those down. The pole has got to look like y, 1, 2. Well, I won't keep writing Z1, Z2, okay? So that should be clear what I mean. So that's Y, Z1, Z2, Y2, 3, and Y3, 1. Okay, so it has those kind of denominators, all right? But what is the numerator? First of all, what's the form part? So this is something, if you haven't seen before, it's a little bit cool. Let's even talk about it in P1. Okay. So this is just a quick aside. This is a quick aside. A quick aside on forms in projective space. So let's say I'm in P1. So that means I have some vectors y, which are 2 vectors, I equals 1 to 2, which I can write as, let's say, 1y. Now, what's the most obvious form that you would associate with that? The upstairs would be something like dy, right? But how can I write dy? How can I possibly get dy if all I have at my disposal are capital Y and the epsilon symbol? I mean, there's nothing special about that bottom component of Y. I could have rescale the bottom component to be 1 and have the top component. I could do any other rescaling, okay? The answer is the following. The form is actually, and it looks a little funny when you first see it, it's y dy. There's a y there that's contracted with the dy. If I'm explicit about this, it would be yi dyj epsilon ij. Okay? And so let's say I wanted to write down a form on P1. Well, the kind of d part has to have this y dy. So first let's see why does this work? Y dy, so this would be like, y would be 1y. dy is d of 1, which is 0, and d of y, which is dy. And now I'm supposed to take the determinant of this, right? Which is 1 times dy minus y times 0, which is dy. Okay? But let's say I have a form, it has a y dy upstairs, but whatever I'm doing with it has to be invariant under rescaling y. So this picks up, if I send y to ty, this goes like t squared upstairs. So just in order for it to make sense, there has to be something with like 2 t's, with 2 y's downstairs. So for example, I can have over ya, yb, where these are also 2 vectors. Okay, so that's a good example of a form. This is now fine as far as the weights in y are concerned. It still has some weights in a and b though, right? So I can make up for the weights in a and b by putting an ab upstairs in the end. Okay? So this looks a little bit fancy, but you know, here is my P1, here's my point A, here's my point B, and what I've now done is written a form, I'll just write it again, y dy over ya, yb, ab, right? Now what happens if I put A is equal to 1, I don't know, alpha, B equals 1 beta, and Y equals 1y, if I just set those coordinates, use rescalings to get to those coordinates, then this form becomes, the upstairs is dy, the downstairs, this ya becomes like 1y, 1 alpha, this determinant, which is alpha minus y, beta minus y, and meanwhile the numerator ab becomes alpha minus beta. Right? And that's exactly dy times 1 over y minus alpha minus 1 over y minus beta. That's exactly what we call the canonical form of the interval before. Okay? We can also call this, we can also notice that it's the d log of ya over yb. So that's one of the beauties of doing things projectively, is that by the time you've written down an object that has the correct weights, you're almost always done, okay? Or very close to a done. All right, now let me just take a second to explain why you have this y dy, because it's kind of cool. You see, when we are dealing with projective space, we keep saying that we have to have an invariance under rescaling, right? But if I want to form on projective space, that means I want to be able to compare 2 nearby points. But they can have different rescalings. In other words, my form has to be invariant under not y, not just y goes to t, you know, yi goes to tyi, but it has to be invariant under t of y times yi. It has to be invariant under a local GL1 transformation. Because after all, this point, you know, has its own private rescaling, a nearby point has its own private rescaling, if the form is going to be well-defined on projective space, it shouldn't just be invariant under a global GL1 rescaling, but under a local GL1 rescaling. And that's non-trivial. So under local rescaling, dy goes to t dy plus dt y. And the t part, that's the same as the global part, that's fine. So long as everything has the correct weights, that will cancel. But the dt part will not cancel in general. Okay? Let me give you a dumb example. I could have gotten another way of getting 1y here. Another way of getting dy would have been to write down, I don't know, 1, 0 dy. Okay? 1, 0 dy is exactly, this is d little y, right? Just this is 1, 0, 0 dy. This is dy. Okay? This is clearly very stupid, though, because here I'm putting in ahead of time, you know, I'm putting in that I've gauge fixed with the 1 upstairs rather than the 1 downstairs and so on, right? So what's wrong with this form? This stupid form is not invariant under local transformations, right? Under this part, it won't be invariant. The only way to make it invariant is such that wherever you have a y, a dy, there should be a y, it should be in a bracket with a y, so that the anti-symmetrization of that y will always kill this extra term. So that's why y dy works. Because this part goes like dty, and the y's antisymmetrically contract to 0. Okay? So that's a very cool thing in any projective space. The form on any projective space, just a general fact, on Pn, a form looks like y, and then just one y, and then n dy's. This would be a top form. And then it's just multiplied by some function that has weight minus n plus 1 in y. Okay? And that's what any top form, any n form on Pn looks like that. So it has this funny y, dy, 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 dy structure. And when you choose a coordinate chart to set somebody to 1, it just becomes dx1, dx2, etc. The usual obvious form that you'd have. Okay. Now, with all of that, let's now return to our triangle. Yes? Yes, yes. Yes, no, it was not obvious it had to be D-log form. In fact, this is something kind of cool, and we'll, yes. I mean, you get used to it in these small examples, but this is it's a very interesting thing that there are some presentations, for example. So let's do the triangle, and I'll make a comment about it there, and then say a little more about it. So if we want to do the form for a triangle, okay, what's the form for a triangle? We'd have, if one exists, it would have to be. So now we'd have to have y dy dy over. Now, what are our poles? We have to have y1, 2, y2, 3, y3, 1. Okay? And then upstairs, now we have to make up the weights in 1, 2, and 3. Right? So how do I make up the weights in 1, 2, and 3 in this example? There's weight 2 in each one. So all I can do is do 1, 2, 3 squared. Okay? See, it's really nice because now you can choose any points that you want. You just shove it into this formula. You immediately have the form with the numerator and everything, right? Okay, but it is indeed the case that this is actually d log of y12 over y31, d log y23 over y31, wedge, okay? So there's a way of making it manifest that it's a d log form by writing as d log, wedge, d log. But it's interesting, every way of writing it manifestly as a d log form always breaks a little bit of symmetry. See, if you're going to write as a d log form, it has to be some ratio of things, right? Because everything has to be invariant under rescaling. It has to be invariant under rescaling in y. Never mind these guys, but because the d's are hitting y, so it has to be invariant under rescaling in y. But you have to choose somebody special. 3-1 is special, and it's the ratio to the other ones. And you could choose anyone to be special, and you'll get the same answer up to sign. Okay? But this is the sort of simplest manifestation of a very general phenomenon that often our forms can look very simple and symmetric, written out, but not manifestly d log. You want to make them manifestly d log, you always make some choice to show it like that. Okay? All right, so that's the canonical form for a triangle. So let's look at canonical. I'm just going to write two formulas down. Canonical form for triangle 1, 2, 3 is 1, 2, 3 squared over y12, y23, y31, and then there's this universal y d squared y factor. Maybe because it's universal, I'll put it on the other side. Now, let's write underneath it the formula that we just saw, we're just talking about for the R-invariant of 1, 2, 3 in this sort of toy example that we did for our toy amplitude a moment ago. This was delta squared a to 1, 2, 3 plus a to 2, 3, 1 plus a to 3, 1, 2 over 1, 2, 2, 3, 3, 1. Okay. They look somewhat similar. Okay. Both of them have these factors downstairs, and both of them have something squared upstairs. Remember, this is a Grassmann delta function. So a Grassmann delta function is literally the square of this expression. You write it down as a Grassmann expression, and you just contract the indices. It's a Grassmann delta function. So we have something squared over 1, 2, 2, 3, y 3, 1, something squared over 1, 2, 2, 3, 3, 1. All right? And now here, just given the amount of time I have, I can't describe it. I can't tell you much more conceptually where this comes from. So it'll just have to look like a little bit of a trick for now, okay? But I want to at least show you how these things are actually really explicitly connected. So first of all, how could I, and there are some other funny things, right? Here, the z's are 3 vectors. Here, the z's were 2 vectors. On the other hand, here I have a y, and here I don't. So it's obvious what's going on. Y is a vector, right? So y is going to define what is the 2-component part and what is the third part. In other words, whatever y is, imagine that I write it as like 0, 0, 1, So maybe I'll do it the other way. Yeah, no. Imagine whatever y is, I'm going to write it as 0, 0, 1. And the z's I'm going to write in this basis. I can always do an SL3 transformation to take it to that basis. So this is not asking for anything, right? This is just defining what I mean by these guys. I'm going to write the z's upstairs as the two-component vectors, and downstairs as something, I don't know, I'll call it xi for the bottom component. All right? Okay, so first of all, what is y12? Well, y12 is just the just a determinant with 1 there, so it's just the 2 by 2 determinant made from the little z's here, right? So y12 would just be little z1, little z2, and so on, okay? y23 would be little z2, little z3, where this is just the determinant made out of the little guys. But the most interesting thing is, what is z1, z2, z3? That's this determinant. So that's this determinant that's like z1, z2, z3, xi1, xi2, xi3. So what is this determinant? This determinant is equal to xi1, 2, 3, plus xi2, 3, 1, plus xi3, 1, 2. Okay, that's just expanding the big determinant. All right, so if I strip off this yd squared y part and I just look at this part that's left over, if I make that choice where y is 0, 0, 1, now this is looking extremely similar, right? Now this is xi1, 2, 3, plus xi2, 3, 1, plus xi3, 1, 2, all squared, divided by little 1, 2, 2, 3, 3, 1. Almost there. Still not quite there because the x's are just bosonic variables here, right? But of course, downstairs, the etas are fermionic variables. But it's very close. What I'm going to do is I'm just going to say that each xi, like xi1, is going to be some fermionic variable phi dot eta 1. But this is going to be, the etas is going to be a 2 vector, 2 components, and phi is going to have 2 components. And similarly for xi2 and xi3. So A runs from 1 to 2. So what am I doing? I'm saying that, what I'm really saying here, sort of geometrically, is that the z's, the y points in some direction, and I'm imagining that the z's are such that they're something generic in the other directions, but in the y direction, they're infinitesimal, they're small. These x's are phi dot eta, where both phi and eta are Grassmann. That means that xi to some power is equal to 0, right? So this is kind of a way of saying that in the direction of y, the z's are kind of small. I'm only interested in some Taylor expansion in the neighborhood of where the z's in the direction of y. But the big directions of z are sort of orthogonal to y. That's, they're the ones that are totally unconstrained. Okay, in any case, if you do that, so I'm just taking these x's and I replace them with phi dot eta 1, phi dot eta 2, phi dot eta 3. Okay, and finally, if I take this expression and I do a Grassmann integral d squared phi of it, that's exactly equal to this. Okay. So basically the d squared phi part just pulls out of it the part that's quadratic in the etas, and that's exactly the delta squared part. Okay, so it looks like a bit of a procedure, and this is actually historically how it was done. this sort of observation was made. And later we understand what this is really about. I mean, so this is about something very simple and canonical in kinematic space. But I probably won't have time to explain exactly what it is, but I just want you to see that there is this concrete connection. Okay? So what have we seen? We've seen that this sort of toy R-invariant is essentially up to this little dictionary with the phi and eta and so on. This toy R-invariant is the canonical form, the D-log form for a triangle. But the z's of the triangle are one higher dimensional, and the one extra component is where this kind of SUSY is living. Okay, the one extra component is where the etas are living. The phi dot etas are living. All right. Well, actually, since I'm here, let me tell you. Let me tell you yet another way that you can go from this canonical form to the superamplitude, to the R-invariant. Sorry. Okay. So when we write the formula like this, this makes it appear like it depends on y and z, as well as, I mean, y and z in these combinations, right? Suppose for some reason I somehow give you a formula function where the only place where the z's ever occurred were inside, with a y in them. So let's say I have y, blah, blah, z, y, blah, blah, z, y, blah, blah, z. What does that mean? That means that by the time I put y equals 0, 0, 1, I will only ever get a function of the top two components of the z's. The bottom components will drop out totally, right? Well, this, of course, doesn't look like that, right? Okay. And remember, this is omega on y. It's a canonical form on y. But remember, I also told you that this is the d-log of y12 over y13, let's say d-log y23 over y13. Now, in this expression, the d is thought of as hitting the y. I imagine the z's are some kind of fixed things, and this expression, the d is hitting the y. All right? But now we're going to let our imaginations roam and wonder what would happen if we just let the d hit everything in sight. Okay? If we let it hit everything in sight, then we will also have terms where some dy's and some dz's, and we'll have a term where the y doesn't hit the z's, the d doesn't hit the y's at all. It only hits the z's. So let's look at that term. Let's look at the term where the y only hits the z's. All right? Well, in the term of the y only hits the z's, that's exactly like what we were saying before. The z's and everything to do with the z's always appears with a y in front of it. Okay? So that part of the form where the d's only hits the z's and not the y's, that part I might as well write. So if I now let it go and look at the part now with only dz's, if I put z is equal to the 2 vectors z and the xi downstairs, well, the x's drop out totally. There's no xi there anywhere, right? And this expression will instead become the d-log of just the little 2 brackets up here of 1, 2 over 1, 3, d-log of 2, 3 over 1, 3. Okay? And, well, if you work this out, small exercise, you will find that this is dz3, dz1 I 2, 3 plus dz2 I 3, 1 plus dz3 I 1, 2. Same thing j, epsilon ij over 1, 2, 2, 3, 3, 1. This is on the nose equal to the R invariant 1, 2, 3, where I take eta and I replace it with dz. You want to know where the anti-commuting things in SUSY come from? What anti-commutes? Differential forms anti-commute. Okay? So in fact, instead of thinking about the superamplitude as a function of z's and a bunch of super variables, we can think of the about the superamplitude literally as a differential form on momentum twistor space. Isn't that cool? Okay. Yes. 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 No, that's right. For some reason, in that picture, for some reason, what we're doing is only looking at what multiplies at this function. Okay? So we have y d squared y, but that's a canonical thing to strip off. After we strip it off, we look at the function of what's left, and we do this funny procedure. Okay? Now, as I said, this funny procedure has a rationale, but this other thing that I'm telling you is a little bit more directly what we're after. Okay? Because let's say you forgot about all this stuff, and someone told you you have a bunch of component amplitudes with different helicities, and you want to group them together into a unified object, right? Let's say even in terms of lambdas and lambda tildes. Well, what's the problem? The problem is you have some negative helicity gluons, and there's some positive helicity gluons that just have different helicity weight. So how could you possibly combine them into the same object? Well, you could take the m minus and just multiply it by d squared lambda tilde. You take the m plus and multiply it by d squared lambda. And now this differential form has taken care of all the weights, and you can add them all up meaningfully. And you can also extract any individual component that you want by just going back and looking at that piece of the form. Okay? So in one direction, starting with a superamplitude, you can trivially build a differential form on momentum twistor space directly. All you do is you take every eta and you replace it with a dz. Okay? The fascinating thing is that there's a d-log form on momentum twistor space. The y is gone. This is directly a d-log form. Sorry, here is in this toy example. We'll do the momentum twistor version in a moment. But there's a differential form on kinematic space, directly on kinematic space. And you can read off the different helicities from the pieces of that differential form, and you can think of that differential form as directly being the superamplitude. Okay? So one of the annoyances about supersymmetry all the time that people complain about is it makes geometry a little super, infinitesimal, anti-commuting, right? Not here. They're just flat-out forms, just the dumbest thing they could possibly be, right? So the superamplitude is literally a two-form in this case. In n equals 4 Superang Mills in general, in this momentum twistor language, it's a 4 times k form. Okay, it's a 4 times k form on momentum twistor space. Okay, but what this form is, you see, on Y, this form had a very beautiful interpretation as the canonical form on a triangle. Okay, the translation of canonical form on triangle into what is this form on Z space is a little bit more interesting. And it actually, it involves an idea very similar to what we saw in the story of the isosahedron. That now in kinematic space, we have a positive region. The positive region is now specified by these z's are some vectors. For example, in this case, in this two-dimensional case, well, we haven't gotten to the amplihedron yet, but in this two-dimensional case, well, yeah, let me not jump jump ahead yet. Sorry, that won't make much sense. I just wanted you to see, though, that there's a couple of routes. There's a sort of a slightly artificial seeming route, but which has a good explanation I have time to get into. There's this more direct route to go from a canonical form to the actual superamplitude. Okay? That's all I want you to see so far. Yes? Sorry? That's the whatever it was called, the unwinding the amplihedron in binary paper. Yeah. Yeah. Okay. Yeah. Well, the amplihedron is a little hard enough to get used to, even in this more conventional Y picture. But nothing in it is hard. It's just all slightly unfamiliar. Okay. So let's return then to our toy example. So if you give me an n-gon, and I just, again, blithely am drawing this sort of convex n-gon like this, then if I look at the canonical form of this n-gon, then it could be the sum of 1 I plus 1. That would be one way of doing it if I triangulate it like this. Right? So the object fundamentally is the canonical form of this n-gon. You can triangulate it in many ways that you want, but the canonical form for it is such that when you convert it to the superamplitude, you get our toy R-invariant formula. Okay? So what the object is fundamentally is the canonical form of the n-gon. That's its symmetric God-given presentation. And you can break it up into pieces in many ways, any ways that you like. Okay? But before generalizing this, so that's the amplihedron in this case. So this would be the k equals 1, m equals 2 amplihedron. If you know about what those integers are, it's just a polygon in this case. We haven't gotten to the Grassmannian world of amplihedra yet. We probably won't tonight, but we'll do enough so that you'll know what to look for in it. Now we want to generalize this to higher dimensions. And again, the sort of key idea was that the z's are like a little z as well, and then there's this extra component, this CA equals phi dot a to a. Oh, sorry, I'm writing so poorly there. Phi dot a to a. Okay, and we have y, which we set to 0, 0, 1, and the canonical form is equal to y d squared y times some function of y, and from this function of y, we could go to the superamplitude. But there's a bit of unfinished business here, which is we again just draw this picture like this: 1, 2, 3, 4, right? It's crucial that it's a convex polygon. You know, if it looked like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Then if I look at the sum of 1 I plus 1 is just garbage, right? So it's really crucial that the external data, the z's, are in have some nice property, that they're automatically in this convex presentation. Okay? Now think for a second. How could you decide, if you're blind, if someone handed you all the vectors and you refused to plot them, how could you decide whether, in fact, those points were convexly ordered or not? Okay? And there's a very beautiful way of doing it. The points are convex so let's draw this case. You see, every triangle in this picture, every ordered triangle, what makes it convex is that every ordered triangle is oriented the same way. every ABC, every ordered ABC, they all have the same orientation. That's not true if it was in this random crappy arrangement. Okay? The fact that every triangle is ordered the same means that if you have A less than B less than C, then, for example, B is always to the left of AC, or always to the right, but you make some choice, right? And that means that this 3 bracket, ZA, ZB, ZC, is bigger than 0, so long as A, B, and C are ordered. That's the key thing. And that's what you could just check on a computer without looking. Okay, someone hands you the Zs. If you just calculate all these minors, then you discover that if the minors of the Zs now are positive, of the external data, if the minors of the external data are positive, then you have a nice convex polygon. Okay? So let's summarize what a polygon is, what the interior of a polygon is, in all this language. And then we'll do one more if you're blind exercise. So a polygon, convex polygon, is all the points that look like y is equal to CA, summed over A. So I runs from 1 to 3. The C's are positive. Okay? And we ask that the external data be such that the Zs are positive. Again, crucial, the ordering here. If we don't have ordering, it means nothing to say the minors of a matrix are positive, because the minors are antisymmetric. So what they are depends on the order in which you present them. Okay? If you have an ordering of the columns, does it even make sense to talk about positivity of determinants? Okay? That's the interior of a polygon. Now, one more exercise before we generalize. The most obvious feature of the interior of the polygon is what? Is that the boundaries are 1, 2, 2, 3, 3, 4, 4, 5, and so on, right? The boundaries are not 1, 3, 2, 7, right? They're all consecutive things. And again, we see it in our eyes, but how can we prove it? So I now want to see sort of algebraically, directly from this definition, how can we see that the only boundaries of the polygon are when y I plus 1 goes to 0? So where are the boundaries? Well, let's ask, could we have a boundary at y AB goes to 0? Let's, for the moment, just cheat and draw the picture, because it's obvious what the issue is. So let's say we have AB. What we want to know is there a boundary where YAB goes to 0? If there is, that means that YAB can never switch sign, right? It's always on one side, and when you go to boundary, it hits 0. Okay, but that means that generically, it always has a fixed sign. And what's clear is y doesn't here, because if y is in here, YAB will have one sign. Here it'll be 0. Here it'll have another sign. Whereas, of course, y12 or AA plus 1 always stays positive, and it only goes to 0 when you're literally at the boundary. Okay? So in order to see whether AB is a boundary, we want to investigate whether there's some positivity property of YAB. Okay? So let's do it. So YAB, so Y is C1 Z1 plus Cn Zn, and therefore YAB is C1 1AB plus C2 2AB plus dot dot plus Cn NAB. And this has a chance to be positive because the C's are all positive. And we know that the minors are positive. These 3 by 3 minors are positive too, so long as they're ordered. They have to be ordered. So if they're all ordered, then this will always be positive. Let's say they're not ordered. So let's say one of them is out of order. All it takes is one of them to be out of order, and it cannot always be positive, simply because whichever one is out of order, make that guy's C huge, and the other one small, and it can be negative, make that guy's C very close to 0, the other one's right, and the other will be positive. Okay, so it boils down to the question of whether AB is such that 1AB, 2AB, up to NAB, whether they can all be reordered so that they look like ABC in increasing order. Okay, so let's see if that's possible. Now I'm going to draw. This is not a picture, so it's not cheating. It's just looking. I'm just writing the indices. So here's index 1, index 2, index 3. Here's index A somewhere, and here's index B somewhere. And I'm going to imagine generically they're far apart from each other, just first to see what happens. Okay? So let's look at all these signs. So what is 1AB? That's positive, good. 2AB positive, 3AB positive. But you see, if there's any space between A and B, if there's anybody in here, then star AB will be negative, right? Because it's out of order. So I have to swap 2 of them to put it back in the order. So if there's any space between A and B, I'm dead. Therefore, A and B have to be right next to each other. That's how we discovered the boundaries are when AA plus 1 goes to 0. So these are the boundaries, and the rest of them are not. Okay. Now, let's generalize this to higher dimensions. And we're just going to generalize it to higher dimensions by letting this go to any, I'll write it m plus 1. And crucially, we're going to generalize the notion of the positivity of the external data, again, the only way that we can. We have an ordering, so the most natural thing to do is to ask for the external data to be positive. Note, I just want to make a comment here. One of the interesting things in this story is that the whole story of von Schell diagrams, the positive Grassmannian, etc., there's all kinds of action inside this GKN Grassmannian. All this positivity, all this stuff. But the external data was just a sort of like dumb bystander to all of the action inside the Grassmannian. It only interacted with the Grassmannian via these delta function factors. It's kind of a window into what's going on. What's fascinating here is that we now have to ask the external data also to have positive Grassmannian-like positivity, right? The external data is a 4 by n matrix, all of whose minors are positive. And that's now putting the external world of the external data and the internal world of the Grassmannian now on a more on a closer footing. But anyway, that's jumping to some other things. This is just some polytope. Okay, this is just some polytope. Now these are again famous polytopes. They're called cyclic polytopes. And now we're going to look at the case of m equals 4. Okay. So we did m equals 2 before. And now I'm going to skip m equals 3. Even and odd are a little different, but let's look at the case of m equals 4. Oh, sorry. Final thing I wanted to say. Sorry, before jumping ahead. How do we see, another thing that we have to see without pictures, how do we see that the sum of 1 I plus 1, how do we see that this is a triangulation? Of course, again, we drew it and it's obvious that it's a triangulation, but how can we kind of see algebraically that it's a triangulation? Well, what it means for it to be a triangulation is that if I look at the boundary is the sum of all the I plus 1s that we figured out were the boundaries of the polygon. All right? So let's look at the boundary. So what is the boundary of this? Well, remember the boundary of any triangle ABC is the segment AB minus the segment AC plus the segment BC. Right? The usual notion of boundary. So let's apply it here. The boundary of, so the sum of the boundary of 1 I plus 1 is the sum over I, 1I minus 1I plus 1 plus I plus 1. Okay? So there's the sum that we want, and these terms cancel telescopically in the sum, because there's a minus sign there, okay? So they just cancel telescopically. Okay, now we're done with the polygon. And with all this practice, it's going to come in handy because we can't visualize four-dimensional polytopes, but we can do all the same manipulations on them. Okay, so now let's look at the case m equals 4. And needless to say, this is going to be the amplihedron for our NMHV amplitudes. As we'll see, the canonical form for this object will be the NMHV amplitude via exactly the dictionary that we talked about a moment ago. But this is slightly less familiar, right? And in particular, where is the II plus 1, JJ plus 1 going to come from? What is this triangulation 1 II plus 1, JJ plus 1? That we got from BCFW. We've never heard of BCFW. We're just going to triangulate this sucker, and that's the simplest triangulation we're going to find, okay? So, but first things first, what are the boundaries of this guy? Well, let's ask the question. Now, the boundaries would be some A, B, C, D. Okay? These are now things that live in what? They live in P4. Okay? The previous thing lived in P2. It was a two-dimensional object. This is a four-dimensional object. So the boundaries before were I plus 1, involved 2 guys. Now they have to involve 4 guys. Right? Well, let's again ask the question. I'm going to draw my index loop again here. This is index 1, index 2, index 3. And here there would be A, B, C, and D. N. And let's do the same analysis as before. So 1 A, B, C, D is okay. So again, I have to ask for 1 A, B, C, D, C1 plus C2, 2 A, B, C, D, plus dot dot Cn, N, A, B, C, D. To be positive, is this positive? That's what I want to know. Okay, so 1, 2, 3, this is all okay, but once again, if there's any gap between A and B, we're dead. Right? But, so B has got to be next to A. But now I'm allowed to have as big a gap as I want to the next guy, you see? Because as I go around, I have 1, 2, 3, okay, if it's there, I get 0. If it's there, I get 0. If it's here, now in order to reorder it, I have to skip over A and A plus 1. I have to skip over 2 guys. So that's 2 minus signs, and it's a plus sign again. Okay? So now I can have any size gap that I want to C. But if there's a gap between C and D, I'm dead again. Because in order to reorder it, I have to skip past C as well as AA plus 1. I have to skip past 3 guys. Okay? So what does it have to look like? It has to look like AA plus 1 and then C plus 1. So we've discovered that the boundaries of this object are of the form yi plus 1, jj plus 1 goes to 0. Now that's a very 0th order amazing thing, because nowhere did we ask for that. Nowhere, all we had were these z's. Nowhere was even consecutivity important for anything, right? All we asked is that all the minors are positive, okay? And yet the structure tells you that the boundaries group the z's up into zi I plus 1 and zj j plus 1, which we know we interpret in momentum twistor language as points in space-time that are null separated from each other. Okay? So the most sort of primitive thing that what the structure should do is tell you where the poles are, and why they're local is a consequence of what? Just positivity. Okay? All right? Yes?
What happens if M is odd?
When M is odd, there's the structure is a little bit different when M is even and odd. When M is odd, the notion of, maybe Jake mentioned this, the notion of positivity for the Grassmannian has a sort of I mean, you really order them. So you really say it's like 1, 2 up to n. And so it's literally, it would be like 1, 3, 4, n is positive, okay? Not n, 1, 3, 4. You really sort of order them like that. Now, there's a cyclic symmetry, though, where you rotate everything over, but when the columns have an odd length, you have to pick up a minus sign for the last column when you bring it around. So it's called the twisted cyclic symmetry. And so that's all. When M is odd, when M is even, these guys are genuinely cyclically invariant. When M is odd, they're not. They have this twisted cyclic symmetry. But in fact, when M is odd, this polytope literally gives you the split helicity amplitudes for those component amplitudes. Split helicities where all the -3 minuses for NMHV are right next to each other. And in fact, the split helicity polytope was the first one that Hodges discovered when he first started making the connection between polytopes and amplitudes. So Hodges had this picture that the BCFW terms, the spurious poles, were like facets of things, this incredible insight to think about it like that. And it was first seen in the context of even the NMHV amplitude, where you could literally see it because there are 3-dimensional polytopes. But there, the sort of the early defect was that it was not clear where this polytope was coming from, what it was. You know, you just took BCFW terms and saw you could interpret in this way. And it was, you know, it worked for NMHV, but no one knew how to make sense of it for a higher K. So, you know, 2 things were happening roughly simultaneously within the same sort of 3-week period. One of them was Andrew's picture about polytopes. The other one was the sort of Grassmannian formula. And the Grassmannian formula had the virtue that it was about all K, all N. It clearly knew something, but it forces us to think about Grassmannians, which is not just polytopes, but something a little curvier and fancier than polytopes. And the amplihedron is really the fusion of these 2 sets of ideas, is to figure out that there is some sort of geometric space in which the building blocks glue together. But what's remarkable is that the space has an intrinsic definition and purpose in life. We have not asked to talk about NMHV amplitudes in n equals 4 or take BCFW pieces and glue them together. We've just generalized the polygon in the dumbest possible way to higher dimensions. And it's remarkable that this generalization has this II plus 1, JJ plus 1 property, and even that. And actually, let's triangulate this guy. Okay? So what do you think a triangulation of this guy is? A triangulation of this guy, one very natural one, is a sum of 1 I plus 1, JJ plus 1. Okay? And how can you check? We know all the boundaries are I plus 1, JJ plus 1, so again, you take the boundary operator. And when you take the boundary operator, it has 5 pieces now. 4 of them come in pairs that cancel telescopically, and you have the last one, I plus 1, JJ plus 1, that does not. Yes.
Earlier, from the amplitude side, we had seen that by imposing planarity and locality, we can get this I plus of J plus 1. So now, with this positivity we are getting, so when we demanded it to be cyclic and it is positive this way, this will be planarity?
Yes, it's the planarity is related to the existence of the ordering. Okay, so it's really the ordering which makes the whole thing go. Okay, so yeah. Yeah, here we've replaced locality with positivity. And in fact, also unitarity with positivity, because they'll both come out of positivity. Although here we haven't quite seen, here we haven't seen it yet. Yeah. Okay, I think I have about half an hour, according to our boss here. Where did our boss go? Oh, okay. Our boss has to take me to my hotel. Oh, there's my boss. So it's, boss, do we have half an hour? Half an hour is okay?
Sure.
Okay, great, very good. Okay, and finally, how do we connect to the amplitude? Exactly the same as before, okay? Via either one of the two previous stories, we just add two more rows to our vectors, okay? So the Z is now a 5 vector. The top 4 components are the ordinary momentum twisters. The bottom component is some phi dot eta, okay? And we can, and Y, we can set to 0, 0, 0, 1, and then we can either do what we did before and get the R-invariants, or think about the D's as hitting the Y's and get the scattering amplitude, the superamplitude as a differential form, okay? All right, so that's the story of the NMHV amplitudes, and the case where the amplihedron is a cyclic polytope. Okay, so now comes the generalization, the all K generalization. And by the way, this is all the tree amplihedron. I don't think I'll have time to tell you about the loop amplihedron, although the loop amplihedron is much more interesting than the tree amplihedron in the sense that it has much more mathematically novel than the tree amplihedron. I mean, physically novel as well, but yeah, this is already. I should say that you know, we in our original work, everything was conjectural, of course, checked as good amplitudes people, zillions of examples. And it wasn't until 4 months ago, that a brilliant paper by a group in Israel finally proved that BCFW actually triangulates the amplihedron for the physical case. And it's an amazing paper. They introduced many new ideas, and we're collaborating with them and with Lauren Williams and her young friends at Harvard to actually try to extend this to even generalizations of the amplihedron to higher M, the analog of this M going to even higher dimensions. But it took all that time. It took a good, 8 years to actually really prove that the amplihedron is tiled by cells of, yeah. But anyway, but having done that, I think that they introduced so many wonderful ideas that I think that a lot more progress will be made. But that's all in the world of the tree amplihedron, and essentially nothing is known about loop amplihedra other than physicists' experimental things. I mean, we know lots of things about them. We can triangulate them in various ways and understand various things about them. But they're much kind of more interesting, richer, deeper objects. Okay, but I'll only tell you about trees. Now, we can think of this picture, this formula, in yet another way, okay? And this is actually related to we can think that I have a vector C1, C2 up to Cn. I have a 1 by n vector. I have a k plus, I have the Z1I, Zni. and this was m plus 1 dimensional. We did m equals 2 and m equals 4. Okay? All right. And so I can think of this as giving me the c's being positive. So this is just giving me something in the positive Grassmannian of 1 comma n. Right? In this case, it's just the 1 by 1 minors being positive. So what am I doing? I have the positive Grassmannian of 1 comma n, and I have my external data, which is fixed, but sort of positive in the sense of m plus 1 comma n. Okay? But I'm kind of scanning and varying over, all the possible positive values of the c's. Okay? And what I get in the end is y. Right? But what if instead of having one y, I had a bunch of y's? Okay? So what if instead of having one y, I have k y's? So this index alpha is going to run from 1 to k. And I'm going to just ask each one of these is going to be a linear combination of the z's. But since there's k of these, there's got to be k of these. Same alpha. A runs from 1 to n. And I is going to run from 1 to some big integer, which I'm just going to, this is just defines what I mean by m. I'll just define it to be m plus k. Before we had sort of just k equals 1, and this was m plus 1. So I'm going to say that this is running up to m plus k. Okay? But now I'm going to ask that this y, instead of thought of as just k independent vectors, I really only care about the k plane in k plus m dimensions that it lives in. That's what motivates writing this as m plus k, because I want to make it clear that this thing is always bigger than k. So I want to think about y as a k plane in k plus m dimensions. Okay? So y is going to live in the Grassmannian of k planes in k plus m dimensions. What we did before was k equals 1. So the Grassmannian of 1 lines in 3 dimensions, G1 comma 3, is just 2-dimensional projective space, just the space of lines through the origin. Right? So that's what we were talking about before. And so now we're just generalizing that from projective space into the Grassmannian. Right? So now, in other words, I want to talk about the analog of the interior of a polygon, not in projective spaces, but in Grassmannians. That's the only generalization that we're talking about. So this thing has to be invariant under GLK. I have to do any GLK transformations I want, mix up any basis of k vectors that I want on the planes. And therefore, this C, anything I do with the C has got to be invariant under GLK as well. Right? So the C has to live in the Grassmannian, GK comma n. And now we want some kind of notion of positivity to generalize their positive weights that we had before. Okay. There's just one notion that we can use using everything that we've been doing here. We just have one thing, which is the ordering. That's it. That's the only structure we have. So we ask this to be in the positive Grassmannian. And the z's are positive, again, in the usual sense that ZA1 through ZA m plus k are positive for ordered. That's it. This is the entire definition. Okay? Now, let me go back even to the case of the polygon and point something out that, again, was the last thing that was so intuitive that we did it without thinking. But I want to say it in this language. So let's say that I write y equals C1 Z1 plus Cn Zn, right? So again, this is like C dot Z, right? But the picture is the Z's are fixed, and I'm scanning over all possible C's, so long as they're positive, right? So they have to be in the positive G1n. They have to be positive. Okay, but if you think about it, this is a very, very redundant covering of the inside of the polygon. Because after all, these C's, there's n of them. It's only a two-dimensional polygon. N is 100, right? So there's tons and tons of different positive values of the C's that are just landing me on the same point. This is a very, very redundant covering of the space. How can I get a non-redundant covering of it? Well, I should go down, I should go down in C space to lower dimensional boundaries in C space till the number of dimensions that are sort of labeling the boundary is equal to the dimensionality of the space that I'm trying to tile, right? So in this case, what are we doing? In this case, we have to find two-dimensional cells of positive G1n, because our space is two-dimensional. So we have to find two-dimensional cells of positive G1n. What are the two-dimensional cells of positive G1n? They're just, it's so trivial in this case, I just set all but 3 of the C's to 0. Okay? So the two-dimensional cells, so the 2D cells of G1n look like C's that are zeros everywhere except in 3 slots, A, B, and C. CA, CB, CC. Sorry about that. There's 3 of them, but remember it's up to GL1, so I can always set one of them to 1, up to GL1, right? Okay? Okay, so these are the cells that non-redundantly map into the amplitude, which is just the polygon. But what does any one of these cells do? Any one of these cells, well, here's a triangle A, B, C. Any one of these cells is not covering the whole amplitude. It's not covering the whole polygon in this case. The image of any one cell is a piece inside the polygon. All right? So you could just look at the collection of every triangle, every two-dimensional cell in the positive Grassmannian, and you can look at what its image looks like under this map. Every two-dimensional cell is some random triangle. So you take all these cells, you get all these shards, all these triangles, right? Now someone comes along to you and says, oh, there is a cool collection of cells of the positive Grassmannian that you should take that do something good and nice and we like it. They look like 1 II plus 1, say. Those cells, those two-dimensional cells. And you say, what's good about those cells? And inside G1n, there's nothing good about them. Okay, you have this 1 I plus 1. There's nothing special about them. They don't glue to each other in any way. They don't do anything special. Where they do something special is those cells, their image under the C dot Z map, right? Their image, those cells map into a triangle that lives inside the polygon, which is the amplitude in this case. And there are various collections of cells on the Grassmannian side which map into a triangulation on the amplitude side, which is just a polygon in this case. All right? So what's the analog here? Here, the amplitude lives in an, what's the dimensionality of GKK plus M? It's K times M. Okay? So the amplitude lives in a K times M dimensional space. The amplitude is K times M dimensional. Okay? So we can look at collections of K times M dimensional cells of the positive Grassmannian GKN under this y equals c dot z map into what we used to call triangles, but Lauren Williams and friends like to call tiles, which is probably a better name, tiles in the amplituhedron, in the k times m dimensional y space of the amplituhedron. These cells are cells in the sense that Jake was telling you about, okay? You should think of the cells of the Grassmannian as the analog of triangles. In fact, the positive Grassmannian, I forgot to say this, maybe, I assume Jake said this. The positive Grassmannian is the Grassmannian analog of simplex. That's what the positive Grassmannian is, okay? So it's a Grassmannian analog of a triangle, or a tetrahedron, or a simplex in higher dimensions. The amplituhedron is the Grassmannian generalization of polytope, what you get when you put a lot of simplices together to make more interesting, bigger objects. Okay, but the positive Grassmannian is the analog of a triangle. And the point is that the D-log form associated with the on-shell diagrams, or their momentum twister cousins, the D-log form on the positive Grassmannian side here in C space, immediately just gives me a D-log form on Y space, directly by this formula. Okay, because on that cell, the whole point is I'm mapping that cell directly into the correct dimensional region in Y space. So if I take the sort of D-log form on the cell in the positive Grassmannian, it just gives me a D-log form on Y space directly. Okay, and therefore, if I manage to find a collection of cells of the positive Grassmannian whose images under C dot Z tile the amplituhedron, then if I sum their corresponding canonical forms, that will give me the canonical form for the amplituhedron. Okay, so that's the logic. Just perfectly generalizing what we did for polygons. Okay? Now, what's remarkable, again, in this structure, nowhere did I say shift, BCFW. I mean, this is it, right? This is the whole definition. But you can begin with experimentally check, which is how we did it at first. You take all the BCFW terms, you know what they are, so you know what the cells are, and then you just ask under the C dot Z map, this goes here, this goes there, this goes there, and then you just check for y equals C dot Z, which you can define just by scanning over all the possible positive C's, whether every point lands inside one of those tiles, and whether they cross each other. And we saw up to very high points that they never crossed each other and everything was contained in it. Okay, so that's the sense in which experimentally we could see that BCFW was tiling the space. But maybe in my last 15 minutes, so anyway, that's the complete definition of the tree-level amplituhedron. And the canonical form in Y space, you see, it's fancier because the amplituhedron is curvy. These C's have nonlinear positivity constraints on them. So this is a kind of curvy version of polytopes. And it's even a conjecture that even the tree-level amplituhedron is actually a positive geometry. Actually, I guess it's not anymore, thanks to these guys as a proof. Anyway, but it all is, of course. And the way you extract amplitudes out of this, exactly the same. Okay, you get the form. It's the most beautiful way to do it. You get a form. You let the D's hit the Z's, and you're done. It's a superamplitude directly. Okay, so, or you can do it in the previous way. But now, since I have, let's say k equals 2, I have two y's. I have to fix so the y looks like 0, 0, 0, 1, and 0, 0, and 1, 0. Okay, so a little 2 by 2 block of zeros downstairs, and that's it. And the z's now are m plus 2-dimensional, so the bottom 2 components are infinitesimal, and you have to integrate over both of them. Okay, so in general, the bottom k components are infinitesimal. When you integrate over them, you get the n to the k MHV superamplitude in this setting. Okay, but maybe the final comment that I wanted to make that we can actually show in pretty quickly in some example is one reason. Okay, maybe I'll just say some words and not write down too many equations. So one reason you can be confident, one of the early checks, is that, the fact that the boundaries are when yi plus 1, jj plus 1 goes to 0, that argument is exactly the same as the argument that we had before. And it's just that before we just had C1 times something plus C2 times something. And now when you work this out, now you really have, instead of just y, it's really y1, y2, y3 up to yk, right? So it's the whole k-plane there. And when you expand it out, instead of getting the C, you get the minors of the C matrix, which are positive. Okay, so you get the minors of the C matrix times exactly the kind of brackets that we're talking about before, and exactly the same argument tells you that the boundaries that look like A, B, C, D can only look like I plus 1, JJ plus 1. Of course, it could be there are other boundaries that we don't know about, but at least those boundaries look like I plus 1, JJ plus 1. I say that because for m equals 4, we know those are the only sort of codimension 1 boundaries, but we've been seeing in work with these people that for higher m, there are crazy new boundaries that we didn't know about before. So the story for higher m is a lot more interesting. But anyway, the obvious application to physics is for m equals 4. But one thing that you can see from this picture is why is it that when you go to II plus 1, JJ plus 1, why is it that you factorize into the product of 2 smaller amplituhedra? Okay, so remember that's something that we saw from our artisanal associahedron picture before, but I think you see the difference between artisanal and not, right? Here there's no choices. Essentially, once you're in this neighborhood, there's nothing you can do other than this. There we had wave equations, this, that, was a little bit more artisanal. But let me explain why, when you go to the neighborhood of I plus 1, JJ plus 1, you have to have factorization, how it works. Yes?
So initially we were discussing about the original Grassmannian integral in the
yes.
Abdal amplitudes, that the supersymmetric delta function was there just to ensure scaling, and in some other
yes.
there could be some other function. But later on when we did this kind of finding a polytope with this z going, when dz forms become Grassmann variables, that seems very much tied to supersymmetry.
Sorry?
That seems very much tied to supersymmetry.
Actually, quite the contrary. This is something that lets you imagine that something like this might be going on for a much more general theory. Because you see, even in pure Yang-Mills, totally non-supersymmetric, I can think about amplitudes as forms. I can think about a unified amplitude where I sum all the helicity. You see, normally we say, one of the things, at least I used to say, maybe still people say, is that one of the beautiful things about without supersymmetry, how can we unify? Can we unify? I mean, when we talk about component amplitudes, we have these helicities, that helicities, and they just seem like separate objects. That seems like a little bit of a pity. That's one thing which seems like an advantage, as much as you hate to say it if you're an Anschauer person, of Feynman diagrams or polarization vectors, is that it makes you think there is one master object, and you just got into polarization vectors to extract different helicity components. Isn't that nice? Isn't that much nicer than your stupid individual helicity components? Okay, it stings a little bit because, you know, it's a little bit true, okay? But you say, no, fuck you, SUSY, okay? SUSY is a wonderful way to unify everything because everything is put into one multiplet anyway, and so now we're done. So screw you and your polarization vectors, we're doing everything on shell. But without SUSY, then what? And now there's this opportunity to do it again. I don't need SUSY. I can combine all the objects together in one by just taking every negative helicity gluon and dressing it with d squared lambda, tilde every positive helicity dressing it with d squared lambda, and off I go. It's just that there is something special, of course, about the supersymmetric case. When you do that, then, for example, there's this delta 8q that comes out, which means that the form has some piece that factors out of it entirely. And then you get to study the rest and so on. But I think it's a really interesting opportunity to see what do these forms look like, even in the standard model. You can talk about them directly in the standard model. It is amusing that you can't talk about them with gravity, because now with gravity you have something that has weight, -4, and I can't make up for it with a d squared lambda tilde. I can only take 2d squared lambda, d4 lambda tilde is 0. Okay? So many, many indications, there's so many indications that sort of gravity wants something just a little different. That doesn't want to be, the only way to fit gravity in this framework is by squaring Yang-Mills, and okay, that's something. But I think that's very far from the deepest thing there is about gravity. And it hides so many features that are sort of beautifully there in gravity. But anyway, that's just complaining because we don't know it yet. Okay? But this is yet another indication that if you try to do something like this for gravity amplitudes, you can't. But for anything Yang-Mills, fermions, scalars, standard model, go for it. You can go and write the amplitudes in the standard model as a form. It's kind of amusing. It's a form directly on the kinematic space of the lambdas and lambda tildes. Okay. Yeah, but let me just make this a comment. So here we're in this world where we stripped off the Park-Taylor factor. We've gone down to this momentum twister world. So factorization, like what is factorization normally for NMHV? For NMHV, factorization would be, what happens with the k's when we factorize, with the k hats? The k hat is equal to the k hat for the left plus the k hat for the right minus 1, right? That's what happens to the k. So, for example, for k hat equals 3, NMHV, this would be k hat is MHV on one side, MHV on the other side. Okay? So an NMHV amplitude factorizes into the product of two MHV amplitudes. So that's perfectly fine in terms of lambdas and lambda tildes, but you see there's nothing left when we go down to the k world, right? Because k equals 1 is going to 0 and 0 on two sides. So that's why we're not seeing factorization yet in this NMHV case. We see that there's local poles, but it's not quite enough to see that we're actually seeing something on the left and something on the right, because it's a little too boring. We're just getting 1 and 1 on the left and on the right. But if we go to higher k, certainly we should see something, right? So for instance, if we go to k equals 2, already in k equals 2, there's a little bit of something to see. And I'll just show you this. So if we go to k equals 2, then we should have a factorization. So this is k hat equals 4. Then we can have something with k hat left equals 3 and k hat right equals 2, or k hat left equals 2, k hat right equals 3, which means that we should have some n squared MHV thing. So we have an n squared MHV thing that has NMHV on one side, MHV on the other, or the other way around. So how are we going to see this? Well, let me show you how C dot Z manages to give this to you. So let's say we're going to a boundary. So a boundary here, by the way, in this picture, it's literally that we have some I here, and I plus 1, and J plus 1. Okay, so that's what the I plus 1, JJ plus 1 pole looks like. All right. But let's say we have k equals 2, so k hat is 4, so k equals 2. So we have a y1 and a y2. And if we say that y1, y2, I plus 1, jj plus 1, this bracket is going to 0, right? That means that this y1, y2 is like a line in P5 now, right? We have this line, and this line is intersecting I plus 1, jj plus 1. So that in particular means that, like, I can always, without loss of generality, say that y1 lies on the line ii plus 1, jj plus 1, and y2 is somewhere else. Okay? In fact, the argument about calculating the sign of y I plus 1, jj plus 1 actually tells you what the C matrix has to look like when you manage to hit the pole when I plus 1, jj plus 1 goes to 0. It tells you that certain minors of the C matrix have got to be 0. Okay? So it actually fixes the form of the C matrix. Now let me just tell you, the first thing that you learn is the most intuitive one. Like, let's say it's, I don't know, 1, 2, I plus 1, jj plus 1 is 1, 2, jj plus 1, just without loss of generality. What you learn is that the top component, now the C matrix is 2 by n, you learn that the top component of the C matrix is only non-zero in these 4 entries, and everywhere else it's 0. You see, that makes sense, because y equals c dot z. For the top component, it's saying like y1 is some linear combination of 1, 2, j, and j plus 1, which is exactly telling you that y1 lives on I plus 1, j, jj plus 1. Okay? So we have some boundary, so we have a C matrix that looks like this, and some entries down here that I don't know what they are yet. Okay? I don't know anything about them yet. Okay. But notice something cool. I'm going to now learn something about what these guys look like. Without loss of generality, let's say this guy is 1. Okay? Let me expand this out. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So I'm going to put this to be 1, x, I don't know what it is, and these are a bunch of zeros. And then y, z, and these are a bunch of zeros. Now here's something cool. Let's say that anywhere in here, I have something that's not 0. Okay? So by this minor, but all the minors of this matrix have got to be positive, right? By this minor, let's say in here, something is not, let's say 4 is non-zero. So since I put a 1 there, this thing has got to be positive. So they all have to be positive, right? So all these guys have got to be positive. So all of these are positive. And therefore, x is also got to be positive, right? Because these minors also have to be positive. So c has got to be positive. All of these have got to be positive. Anything in here is either 0 or positive, and x has got to be positive. Okay, and by the same token, y has got to be negative, right? Because this minor has got to be positive. So let me say that that's a minus, so that y is positive now. And z has also got to be positive, right? With a minus sign. Okay, but now let's look in here. Let's say any one of these guys, this guy, alpha. From this minor, alpha's got to be positive. But from this minor, alpha's got to be negative. So everything's got to be 0 here. Okay? So one option for what the matrix could look like is that it's something positive on this side and 0 on that side. Now, what does it look like down on the bottom here, where I just have a 1 by n matrix, where it's positive over here? That's the NMHV amplihedron. The k equals 1 amplihedron. And what is this guy that's just nothing? So one option is to have what it looks like is an NMHV amp. For the rest, for the part that isn't locked, one start looks like the NMHV amplihedron times nothing, or the other way around, right? I could have anything non-zero here, and it forces a 0 there. So that shows how this is the first inkling that the nonlinear positivity is actually forcing factorization. And in fact, what you can show very easily, this much is very easy to show, is that just being on the boundary forces the C matrix to look like the following. If it's I plus 1, blah, and then JJ plus 1, blah, that it has to look like something non-zero here, and 0 everywhere else. And then it has one block that looks like that, and another block, and this overlaps on JJ plus 1, and another block that looks like this. Yeah. Okay, and this is some K1 and some K2, and the rest of these blocks are 0. Okay. That's kind of a cool thing that you can show, that just from the positivity and nothing else, by the time the top row looks like it has the II plus 1, JJ plus 1 structure, the rest has got to sort of almost factor. Now notice it doesn't quite factor. It has these overlaps on columns, and that's necessary because there is this internal particle that's glued across the two of them. Okay, so they're not totally factorized. There's this internal particle that's glued across the two of them, and the presence of those overlaps in the C matrix precisely accounts for that. Okay. But that's just to give you an idea that just the most basic thing, that you got to have something on one side and something different on the other side, is just a trickle-down consequence of positivity. Yeah, I think that is all. That is all I'll say. I don't think I'll have. Yeah, I shouldn't say anything. If I start talking about winding numbers in kinematic space, we'll be here till 4 o'clock. So, all right. So I think I'll stop there. Thanks a lot, guys.
Thank you. Thank you. Please, question. Sorry.
Nima? So you talk about this loop level, or this loop amplitude-hedron, but you also discuss how the amplitude-hedron is very much based around this idea of on-shell kinematics, whereas loop things seem to inherently have off-shell things going on.
That's what you think. They don't. Yeah, that's what you think, yes. They're not, no, they're built out of on-shell ingredients. That's the, you see, I mean, that by now is a very old thing. But maybe it's actually, you actually already see it at tree level. Oh, sorry, yeah, I gotta use this. You already see it at tree level. Never mind. No, I mean, the fact that, I don't know if Jake talked about the loop level BCFW recursion. It's just an example of how on-shell things determine the loop integrand. But I just want to emphasize, this has nothing to do with loops. You would make this complaint already at tree level. Let me draw something. Very likely Jake emphasized this point, but let me just draw something. Let's say we're talking about tree level 4-point gluon scattering. In Feynman diagrams, I have these diagrams, some contact term, right? Okay, and so here we have our virtual particles. You don't need to get to loops to get exercised, right? Crucial in our usual way of thinking about things is virtual particle in the middle there. So how the hell are we getting virtual particles without virtual particles? Okay, well, what is the on-shell diagram representation of this 4-point function? This looks like a tree. Okay, what would an on-shell diagram that looks like a tree look like? Maybe I glue together 3-point vertices and it would look something like this. This is not a 4-point amplitude. This is a factorization channel, right? So the 4-point amplitude already is an on-shell diagram. It looks like a loop. That's what's kind of crazy, right? That is the on-shell diagram for the 4-point tree amplitude. It looks like it has a loop in it. What's going on is I'm getting the effect of this virtual particle by exchanges of multiple on-shell particles. Okay, at the most primitive level, that's why it's not obviously garbage. And of course, but what's so interesting about this picture is that this one picture has both the poles in it, both the channels in it. You don't need to sum over channels separately. And how do I see it? Well, if I want to see where the singularities of this are, I have to erase edges, as I'm sure Jake explained. And I can erase this edge and get the S channel, or I can erase this edge and get the T channel. But this one picture, as a loop, has everything in it as a tree. Okay? Now, just so you know, let me now tell you what is the 4.1 loop amplitude, at least in n equals 4, as an on-shell diagram. I don't know if Jake drew this picture for you. It's what I like to call the Star Wars diagram. This betrays my age. That's the 1 loop amplitude. We did nothing other than just add 4 bridges to the outside of this picture. Okay? It's because it's like when Luke Skywalker is going into the Death Star, you know. That's, you guys don't even know who Luke Skywalker is, I'm sure. Okay, and in fact, when you do loop level BCFW recursion, every term looks like an on-shell diagram, just where you have more faces than there are delta functions. So there are variables left that you have to integrate over, and that's what the loop integrand is. But everything is on-shell. Everything here is on-shell. See, I added 4 edges, I added 4 faces. There are 4 variables that are not determined, so I integrate over them. That's the loop integrand.
Is it not a leading singularity?
Huh?
Does it?
This is not a leading, well, I mean, they're all on-shell forms, if you like. But a leading singularity is often referred to something where you really finally get a function at the end. Okay? So leading singularity is where the number of delta functions is such that in the end you completely lock the momenta, all the edge weights in the diagram. Okay? Here there are just more variables. And so there's a form lying around. And so it's an on-shell form, but it's not a leading singularity. If you like, you could make it a leading singularity by taking this thing and there are 4 extra variables, and you can take residues on them. You could take residues on them to send them all to 0, and then it would take it back to a leading singularity. But you don't have to do that. I mean, so what it really is some, and in fact, let me just tell you the sort of coolest thing here. So, you know, just one of the charming things about this business is how many ancient objects that we've looked at for ages had sort of messages for us. So let's look in the most basic case, just of the box diagram, right? So massless. So I have L plus P1, L plus P1 plus P2, L minus P4, right? And so you write this as, what am I doing? I'm integrating D4L, L squared, L plus P1 squared, L plus P1 plus P2 squared, L minus P4 squared. Okay? So that's the form. That's the loop integrand. That is the form. All right? Okay. Well, what's somewhat striking is that this is a D-log form. Now, this is one of those things that if you're super dumb, you get going in the right direction, and if you're slightly sophisticated, you get discouraged, and then the right answer is closer to the super dumb answer, okay? So how would you write down a D-log form for this if you were very, very dumb? You would say, oh, it's obviously a D-log form. Duh. There are 4 propagators downstairs. There's a D4L upstairs. It's D-log L squared, D-log L plus P1 squared, D-log L plus P1 plus P2 squared, D-log L minus P4 squared. Okay? And then your your curmudgeonly advisor will say, what the hell are you talking about? What is d log L squared? L squared has units. This is moronic, right? There is no such thing as d log L squared. There has to be somebody downstairs just to make up the units. It has to be d log of something dimensionless. Okay? Okay? Go away and stop bothering me with your dumb ideas, right? So, but in fact, and is there any L, what could you put? Well, you could put any one of the other propagators and then you're screwed, right? Because one of them would go to 1. But the wonderful thing is that, in fact, this is very close to the right answer. There are special values, there's special L stars. And that L star is the special value of the loop momentum, which is what you get when you put all of these 4 propagators on shell. Okay, so if you just solve for L squared equals L plus P1 squared, you just put them all on shell. There are 2 solutions to that problem. I don't know if Jake talked about this. If he didn't, just give me 2 minutes. But anyway, there are 2 solutions to that. And you could take any one of them and shove it in here, and they'll just give you this same form up the side. But these loop integrands were secretly d-log forms all this time. But where does this come from? In more complicated cases where you can't just guess like this comes exactly from these on-shell diagrams. Okay? You can actually determine that these variables that occur, these extra variables here that occur in the on-shell diagrams are exactly these interesting combinations. So it's the connection to the on-shell recursion that builds for you the loop integrand as a d-log form explicitly. Okay. A final little comment that I'll make, since I brought up this problem, and since we talked about momentum twisters, this is something to like play with at night as you're falling asleep. Let me give you essentially exactly the same problem. So here's the problem. Imagine that you have 4 points in Minkowski space. It can be complexified Minkowski space. Okay, so it's just 4 complex points in general. And your challenge is the following. How many points are there that are null separated from all 4 of those points? Okay, the 4 points are generic. They may or may not be null separated from each other. You have 4 generic points, and you just want to know how many points are there that are null separated from all 4. Okay. It's clear that there are the solutions in points, because once again, it's 4 equations to be null separated. X minus x1 squared equals 0, x minus x2. So there are 4 equations for the 4 coordinates, x. So clearly there are some solutions in points, but how many solutions are there? I mean, if you're super naive like me, you would say 16, because there are 4 quadratic equations. Each one has 2 solutions. Probably it's 2 to the 4th equals 16. Okay, and that's very, very wrong. But the correct answer is 2. Okay, there's always 2 solutions to that problem. And you can do it algebraically pretty easily, but you know, if you imagine doing it like in the usual way, you're thinking of drawing light cones or maybe writing formulas, quadratic equations, right? The beautiful thing about momentum twisters is it really trivializes sort of space-time process relationship intuition. Because you never have to draw pictures of light cones or intersecting in sort of curvy, complicated ways. What does this question turn into in momentum twister space? Every point in space-time is a line in 3 dimensions, is a line in P3. So the question is, if I'm given 4 generic lines in 3 dimensions in P3, 1, 2, 3, 4, any 4 lines, how many lines are there that intersect all 4? So now you can think about that question as you fall asleep. This question is the very, very first, this is in a sense the question that really started enumerative algebraic geometry. It's called, the person who started asking these questions was Schubert, not Franz Schubert, some other Schubert. And the method that he developed to count these solutions are called the Schubert calculus, and it spurred the development of algebraic geometry in the mid-1800s. But I'll give you a clue. To begin with, imagine that the 4 lines are not totally generic, but make your life easier by having them sort of intersect each other a little bit. And then, and there are simple enough situations where it's very obvious what the answer is. And then you can argue that the number of solutions can't jump discontinuously as you move things around. So once you have the solution for the slightly special case, you know the solution in the general case. Okay. I would say the kind of #1 thing that's needed if you want to work on these amplitihedral things, the #1 thing that's needed, which is unfortunately also the #1 thing, which I think is the biggest like local barrier, is you have to play with these pictures of points and lines and planes and learn how to intersect points and lines and planes in P3 all day long. And it's high school level stuff. And in fact, it was taught as high school level stuff up until the 1940s and 50s in a lot of, certainly in the UK. But at some point, people decided that kids in high school should learn calculus instead of projective geometry. And so that's, but it's really simple stuff. But you have to not just sort of know it like, oh yes, I know z up to t times z, but you have to live there. You know, you have to be able to take a bunch of points and find where they intersect and intersect this plane and just intersect planes, points, and lines like a motherfucker, you know, all day long, right? That's what you have to like be good at doing. You don't have to be that good at doing it, but you have to have some familiarity with it. But it's really useful. It's really useful for even a lot of these questions about cuts of integrands, for even very practical people who don't care about these things. Thinking about the structure of the cuts of loop integrals in this language is very, very clarifying for what's going on. And so that's why a lot of even very practical people have started think in this way. It's actually quite. As I said, even when you don't have dual conformal symmetry, it's useful to think in this way. You just have this extra infinity line lying around, but it makes life really, really easy. Let me just give you a super practical example. You guys know at one loop there's box diagrams and there's triangle diagrams, right? And you even have ladders of boxes at many loops and ladders of triangles, right? Now, it might not be super obvious, but these are identical. They're exactly the same object. If you know the answer for boxes, you know it for triangles. If you know it for triangles, you know it for boxes, okay? Why are they identical? Because the triangle is just a box where one of the points is at infinity. Okay, that's it. If you write it conformally, it becomes obvious. If you don't write it conformally, you think you have these different things. Okay, so that's just one very simple example of where it's actually useful to have this perspective. If you have things like bubbles, it's more interesting because those things have sort of double poles on the line at infinity. So there's a new kind of singularity. They're not captured by d-logs. They have new kinds of structure and so on. But it guides you to a new kind of thing to think about around infinity. That's really a very powerful thing about projective geometry in general, and the infinity twistor idea of infinity in twistor space in particular is that, you know, we often sort of vaguely think about what it means to go off to infinity. But you can go off to infinity lots of ways, lots of directions, lots of, you know, things going on there, and this allows you to be very precise about what it means to sort of go to infinity. So yeah, so I do encourage you to play with this picture and get used to it. It'll pay dividends. Yes.
I was wondering, so the associahedron plays a part in part of this story. So there's a bijection between the associahedron and the permutahedron. And I was just wondering, does the permutahedron play any part in this story, or could it?
Yes, permutahedra and generalized permutahedra play a big role in many parts of this story. But still, I would say somewhat, a little bit tangentially. They haven't played as central a role as you might think. For example, you might think, ooh, permutahedra or permutation invariant. Permutahedra will have something to do with gravity. Permutahedra have nothing to do with gravity, unfortunately. So yeah, they're objects in this general world. They're interesting. It's very good to know about them. I was originally planning on talking about a whole third topic today, which we're not going to even start talking about. But well, given how things went, I'm not sure I would have even gotten to it. But there's a kind of orthogonal story about a very different kind of set of singularities. Not all these singularities that we talked about, both of the association and the amplitude, are about factorization, infrared, long distance, cutting propagators, and so on. Of course, there's a very famous set of singularities that were people concentrated on in quantum field theory first, which were the ultraviolet, right? The ultraviolet logarithms, the renormalization group, you know, all of that kind of stuff. The physics of the UV, I think, to my mind, I've said this many times in schools like this, and I've started trying to put my money where my mouth is by actually working on it. But I think the sort of physics of the UV is the biggest obstacle to the on-shell sort of plan to take over the world, okay? Because, you know, it's one thing when you talk about scattering amplitudes to say that, oh, I can do that with on-shell techniques and I kick the ass of Feynman diagrams. Okay, very good, very nice. We all say it very polemically, or maybe we don't all say it, but you see, that's a case where you're attacking the enemy. If the enemy is local Lagrangians and Feynman diagrams, you're attacking the enemy at its weakest point, because amplitudes are not a local question, right? As we keep emphasizing, they're not a local observable, right? So it's like you're taking your thing that your enemy is the worst at, and you're like hammering away on that. But they would kind of shrug and say, I don't care all that much about amplitudes. What I really like are correlation functions of local operators. That's what I'm about, okay? And in particular, the entire story of ultraviolet divergences, the whole Wilsonian picture that you zoom in, you take a microscope, you gradually zoom out, you look at physics scale by scale, not diagram by diagram, this deep, fantastic picture of the renormalization group is completely off-shell, as off-shell as could be. I mean, you couldn't be more off-shell by saying you take the field path integral, you integrate over modes between here and there. It's like every possible middle finger to the on-shell worldview is given, right, in this way of doing things. And relatedly, it's very Euclidean, deeply Euclidean. In fact, the whole idea that there's this decoupling between short and long distances only makes sense in Euclidean space. It's not true in Minkowski space, because you and I could be, you know, separated by 4 light years. You could be in Alpha Centauri, I could be here, but our distance could be very small. So it's definitely not true. So x minus y squared can be very small, even when things are macroscopically separated in Lorentzian signature. There is no obvious decoupling between short and long distances in Lorentzian signature, but there is in Euclidean signature. So the entire formalism of standard local quantum field theory, in particular the renormalization group, Wilson's picture of the renormalization group, this very, very deep, powerful structure that underlies 99% of what 99% of quantum field theorists think about the world, who don't spend their time calculating quark and gluon scattering amplitudes. This is deeply Euclidean, deeply off-shell, and if you ask an on-shell person, so do you have a good understanding for the renormalization group on-shell? They would have to say, absolutely not. Zero. I mean, it's really embarrassingly bad. So we would like to have some understanding of that from the on-shell point of view, and I think that's where the on-shell program is at its weakest. But at least a step in that direction is to try to understand whether there is some kind of, I don't know, geometric combinatorial underpinning to the understanding of ultraviolet and infrared divergences. And there is, and it's also related to the existence of interesting polytopes with factorization properties of this sort. But they're not associahedra, they're not amplituhedra, there are these polytopes associated with Szymanczyk polynomials. And you know, much of this has been understood by some group of mathematicians and a few physicists for quite a while. But really sort of getting it to work in a unified, coherent way is I think, work in progress that you know, some of my friends and I have just started working on. So I think that's a path to try to see whether, and there, generalized permutohedra show up all over the place. So, but it's not about this sort of long distance singularities. It's about, for a given graph, the way you can shrink subgraphs that corresponds to possible ways you could separate scales from each other that are relevant either for UV or IR divergences.
Thank you.
Maybe a general comment I'll make about the sort of math-physics connection in this business is that mathematics is an infinite world, and somehow, you know, like if you at least my own attitude, which has worked out pretty well so far, is, you know, I'm not a mathematical physicist. I don't know that much about math. But we know what we want to see in physics. There are some things in physics that we want to see. There's some sort of vision for what we want, the kind of objects we expect are out there. And so if you sort of keep focused on what you want to see, and then you don't get too distracted by the 15 million interesting things they're telling you all the time. You say, but what about this? Does it have something like I plus 1, JJ plus 1? No, okay, then I don't care. You know, so and then it's sort of interesting. Then things start happening, and there is something that draws the very different sets of people who talk very different languages together, because you start focusing on the phenomenon. You say, well, I don't know exactly what you're talking about, but my thing, you know, has this, and it has to have this consecutivity and this kind of thing. Have you ever seen something like that? Oh, yes, I've seen something like that before. And then interesting things start to happen. If you just, but it needs to have a certain level. I mean, it's not obvious exactly where the level is, but it needs to have enough specificity so that you're not spending the whole time, you know, learning about all the zillions of things that they have going on. And of course, it's interesting to them because they have zillions of things going on, but the thing that you come in because physics tells you to do turns out to be way more interesting than all the ones that they ever knew about before. So there's a sort of payoff for them in the other direction as well.
Probably last question. Yeah.
In the case of the scalars, you were saying that if we could just make it massive by just shifting the polygon a little. So here, do you expect for the Coulomb branch there would be a similar structure?
One really hopes so, yes. One really hopes so. One clue, which is very interesting, is that the Coulomb branch amplitudes are dual conformal invariant. That's a real irony, is that tree-level Yang-Mills amplitudes are dual conformal invariant in any number of dimensions. They're not conformally invariant except in 4 dimensions. But this hidden symmetry they have in any number of dimensions above 4. So that's one sort of hint that there's something going on. But yeah, it would be fantastic to see some structure in Coulomb branch amplitudes. There is a sort of a, you know, it's a standard thing in amplitudes that you have to go where the data is. And you're not going to make some jump into some grand structure that's going to explain everything before you have any idea what the data actually looks like. So the great thing about n equals 4 is that there was an ocean of data, and it was developed, and you could compute all sorts of new things, and anyway, and then you can start seeing the structure come out. We're very, very far from done, even in n equals 4. On the Coulomb branch, you can count on like 4 fingers how many non-trivial papers there are that actually calculate something interesting on the Coulomb branch. How to think about it, how to organize your thinking. I mean, you know, I think and there were even some earlier papers, but they were in a rather cumbersome formalism for massive amplitudes. And it wasn't until relatively recently that there was a clean formalism for massive amplitudes. And the supersymmetric version of the clean formalism for those amplitudes only was in a paper from, I don't know, a couple of years ago. Sorry? Yeah, that's right. And then, yeah, and then you have to start getting going to see what it actually looks like. There is a clue that it has something to do with the symplectic positive Grassmannian. And this is a funny thing that there's a story of the positive Grassmannian, and that's related to n equals 4. And very soon thereafter it was realized that there's some orthogonal version of where the GLN, there's also some SO thing sitting there, and that's related to ABJM theory in 3 dimensions. It's really amazing because there's no reason to expect any relation between n equals 4 and the ABJM theory. They're totally different. One is the gauge theory, the other one is the Chern-Simons theory. One is in 4 dimensions, the other in 3 dimensions. One of them comes from D branes, the other comes from M branes. They're not especially closely related to each other, and yet in this perspective, they're super closely connected to each other, which leaves the odd guy out, the SP version of the Grassmannian, and it's sitting around. And nobody knows what it's, how to make it connect to something, but every hint is that it has something to do with the Coulomb branch. So there are some. So anyway, it's sitting there for someone to discover what it's for, I think. But that's a huge question. It would be really fantastic to get some progress on the Coulomb branch.
Okay, I think this can go till infinity as well.
Yeah. Okay. Very good.
But thank you all of you. is real end. Okay.